Okay, example 7, it's around about page 182 in your textbook. Got particle P of mass 0.5 kilos moving in a horizontal straight line. At time t, the displacement of P from a fixed point, the origin, or 0, on the line is x. So that's our direction of increasing x. So I'm essentially taking it this way as being my positive direction. Force of magnitude 8x acts on P in the direction of P0, so back that way. The particle is also subject to a resistance of magnitude 4v. So again, we can model that as going back that way. And when t equals 0, x equals 1.5. And the speed is equal to 4, so we'll take v as being equal to 4, and we want to show that it satisfies this equation, which is the equation for damped harmonic motion. So these are essentially F equals ma questions. So acting in the negative direction, I've got 8x plus 4v, and that is equal to the mass times the acceleration. The acceleration is the second derivative. And then I want to add all of this on. Sorry, I did it the other way. Plus 4 times the velocity, which is dx dt, plus 8x equals 0. So I'm just taking that over to there. And then if I times through, or divide through by a half, times through by 2, that takes us to the required equation. So I can't talk, I'm really sorry. I'm a bit hungry, my dinner's in the oven. That takes us to the required equation. And then it's just a question of solving it. The solving it side of things, you should be feeling quite comfortable with, to be honest. And so we've got the auxiliary equation. So m squared plus 8m plus 16 equals 0. That gives you that m is equal to 4, and so the discriminant is 0, and so this is critical damping. So we're not actually expecting any oscillations as such. And x is equal to a plus bt e to the minus 40. And when t is 0, x equals 1.5. So that's going to 0, that's going to 1, and so a is equal to 1.5. If a was 0, I'd probably rewrite this, but we need to differentiate this to get to the velocity. So differentiating the bracket, you get b e to the minus 40, and then minus 4 lots of a plus bt e to the minus 40, and you're told that when t equals 0, v is equal to 4. And so dx dt is 4, and that is going to equal b minus 4a. So you just pick up your two simultaneous equations, solve them. We know that a is 1.5 actually, sorry, so that's just going into here, and so from there b is equal to 10. And so x is equal to 1.5 plus 10t e to the minus 40. We want the value of x when t equals 1. That gives you x equals 0.211. If you wanted to sketch this, you could find your turning points by setting the gradient to 0. I'll let you do that if you want to. I did one on one of my previous examples, and it's actually a stationary point at 0.1. And we know that when t equals 0, x is equal to 1.5. So this one is starting at 1.5. There's going to be a maximum turning point here. And then as t approaches infinity, this e to the minus 40 approaches 0. So we're coming down onto the x-axis. So that's what that graph looks like, but you don't need to be able to sketch them from scratch, so don't worry too much. But it's just, you can see we've got this sort of critical damping situation where you don't actually have oscillations as such.